Thank you for having me here. Thank you for inviting me, Frederic. Today we're going to be talking about MySQL Community Edition at CERN and how we provide it as a service. My name is Abel Cabezas. I am a database engineer. We can call it database engineer, database platform engineer, DBA, with too many things, so it's not an exact role, right? I started my early career as a software developer, and after a short transition as DevOps, I started working at CERN. I changed quite a lot. I work at CERN. CERN is the French acronym for the European Council for Nuclear Research. It's the biggest particle physics laboratory in the world. It sits astride the Franco-Swiss border near the Swiss city of Geneva, and it was established in 1954. It counts nowadays with 24 member states, and it's an intergovernmental organization that doesn't have any profit and that does not do research with military stuff. What you might hear nuclear, but it's not related with nuclear weapons. It's related with the nuclei of the particles. Okay. So our goal is to understand what the universe is made of and how it works. For that, CERN enables a range of world-class particle accelerator facilities. And it also acts as a common place for people from all over the world, from many different nationalities, to push the boundaries of science and technology. The well-known, I guess for most of you is well-known, and biggest machine at CERN is the Large Hadron Collider, or LHC. It's the world's largest particle accelerator. It consists of 27 kilometers of semiconducting rings that lays between 100 and 300 meters underground close to the Swiss city of Geneva. These magnets, these dipoles, can accelerate particles to nearly the speed of light. And in order to achieve this superconducting state, the magnets need to be chilled to minus 271 degrees Celsius, which is almost zero absolute, or temperature colder than the outer space. There is also the other side. There are also other extreme conditions during the lead-ion collisions. Temperatures 100,000 times hotter than the heart of the sun can be achieved. As you can imagine, this big machine produces a big amount of data. It's estimated that it produces around 1 terabyte of data per second when it is running, but only 1 out of 10,000 events is kept. This one out of these 10,000, only 1% of this is kept. So 0.001% of events are kept. This is what is called the initial data filtering that happens at the experiment or detectors level. And then on a second stage, in what we call the tier 0, CERN data center, an initial data reconstruction takes place. Once this data is reconstructed, two things happen. One copy of this data is stored at CERN for long-term archival into tape, and another copy of this data is distributed across the world to 170 different collaboration institutions spread across 42 countries in what is known as the Worldwide LHC Computing Grid, or WLCG. The word grid, it means it's meant to be a metaphor with the electricity grid. When you are at home, you plug your toaster and you don't care where the power is coming from. You just want the power. This aims to be the same. You just, a scientist in Italy or the US plugs its computer to this network. If he wants to get some interesting data about some event that happened in the LHC, and he will just get it, no matter from which experiment, from which part of the world. When we think about CERN, and we always saw the numbers of the LHC, we think that the LHC is all that there is about the accelerators, but it's not exactly correct. This is what we know as the accelerator complex. The LHC is just the last element of this accelerator complex, which is a set of particle accelerators that take the beams of particles to higher energies before injecting them into the next accelerator, being the LHC the last one of this chain. Also, it's worth mentioning that the LHC is not the only particle accelerator that benefits from this accelerator complex. There are also other accelerators, linear and circular accelerators, that benefit from this pre-acceleration phase. And apart from that, there is also more beyond the accelerators. There are tens of projects at CERN that are not that well known, but that have contributed enormously to the society. From this, I took just a small selection. For example, the Medicis experiment has as objective finding special radioisotopes. This is elements which have either too many or too few neutrons, so they are unstable enough to, for example, detect cancer and other diseases. It's also useful for radiotherapy, for combating cancerous cells, healing them without affecting the healthy tissue. Another experiment that I wanted to highlight is the AMS, or Alpha Magnetic Spectrometer. This is a module that is attached to the International Space Station since 2011. It was delivered by the Endeavour shuttle in its last flight. And its objective is to detect dark matter, dark energy, and cosmic rays in order to understand where is that 95% of energy that we don't understand. We do not understand where it's coming from in our universe, right? And the last experiment that I wanted to highlight is the antimatter factory. This may sound as science fiction, but it's science, no fiction. Here is where we craft the most expensive and most scarce antimatter in the globe. 1 gram of antihydrogen is estimated to cost 1 quadrillion euros. It's 1 followed by 15 zeros. And the challenge is not only creating this element, it's also how to store it, because antimatter has a particularity that when it enters in contact with real matter, they annihilate each other. So the only way to confine it is using a magnetic field, and you only know that you have captured when you release the magnetic field and the antimatter element crashes against the wall of the container.
You can store it in a black hole on engine.
I don't know if we can recuperate it from there. Okay, so enough with the physics. We came here to talk about MySQL and IT stuff. So CERN counts with its own IT department, and among other things, we provide databases. We have Hadoop clusters, we have OpenSearch clusters, we have Grafana Mimi clusters, and we also have traditional DBMS. There are 2 main services at CERN providing databases. This is the one where I spend 50% of my time, is the Oracle Database Service. It was established in 1982, and it was the chosen solution for the already extinct LED accelerator, which is the one which tunnels where we profited from to build the LHC. It comes with around 100 database instances, and the idea here is to provide Oracle accounts as a service. It makes use of several Oracle enterprise-level features like Real Application Cluster, Data Car, Oracle Enterprise Manager, and so on. It's a really complex environment, and partly I believe because it's been for more than 40 years around, and it had to evolve along with the organization. So many people is passing through this project, applying their specific patch, and at the end it grew into a beast that nobody can take. So this is one of the things that I'm doing, is refactoring this infrastructure. It is used by critical services, administrative information services, engineering systems, and accelerators. The amount of data that is handled nowadays is around 5 terabytes. The other 50% of my time I spend it in this project is DBOD, which stands for Database on Demand. It was conceived in 2011. At that time, the laboratory employs around 12,000 people. So there were many physicists, engineers running MySQLs in their corners. Of course, if you are not familiar with IT, you install the database and then you forget. What are the upgrades? What are the backups? Nothing. So with the idea of standardizing all of these deployments, my predecessors thought about creating a database as a service. And in 2011, this idea materialized. The idea here is just to maintain the infrastructure, provide new versions to the users, but the users are meant to be their own DBAs. We are just platform engineers in principle, although sometimes we have to put our DBA hats on. It was designed in the beginning for only MySQL, but also in a flexible manner, so it could accommodate other DBMS later, as it was the case with Postgres, Influx, and TCR timescale, although it's just an extension that we also counted as another flavor. It is used nowadays it started as a side project, few instances, but now it's a key service at CERN, which is used by many key applications, like the CERN single sign-on, not only used by CERN people, but also by people from other experiments across the world. Our private cloud based on OpenStack is also using MySQL as a backend. Some detectors of the LHCP, like the Atlas or the LHCP, are using this. Or the WLCG, the Worldwide LHC Computing Grid file transfer service, is using MySQL. And well, the data that we handle is significantly less, so around 150 terabytes. When it comes to the way we deploy MySQL, I would say it's a little bit particular. We made the same question in the other room. How many of you are running MySQL on-premise? How many are doing it with network attached storage? Okay, so it's quite particular. So yes, our database is run on two different data centers that we have at CERN. We install several MySQL binaries per host. We run several MySQL instances per host located. They have memory constraints, but this is the only thing that is limiting each other. There are no CPU boundaries. For historical reasons, as I said, we decided to run the database with network attached storage in order to speed up the process of migrating an instance to another host whenever there was an OS upgrade to be taken care of, simply an issue in that host that you need to fix. You just migrate the instance, attach the volumes to the new host, and you're done. We have currently 5 types of deployment. As of today, has turned into 4 because we finalized our migration from ProxySQL to Unity cluster. But it accounts to single instances for 90% of the cases, application for disaster recovery for some instances that don't really require high availability, but are kind of important in terms of data that cannot be lost. They have a replica in the secondary data center. We have replication to scale out grids because of some schema designs that were not properly designed, let's say, and we had to scale out the grids with replicas. And then MySQL.
Yeah. So you have replicas. I assume you also use network storage. You have like disparity for where, like,
yes.
It's really pets versus cattle, right? You have very specific servers assigned to be replicas, and those specific servers use specific network storages, or how do you manage that?
No, the thing is that we have 4 different storage clusters, and we always make sure that the host is in the same area of the data center as the storage, so there are not many switch hops. And we also make sure that the primary and the replica are not inside the same set of physical machine as the storage cluster, so they are not dependent on the same stack, let's say. So so I said this started as a side project that didn't accommodate many critical databases, but when I joined in 2019, the SSO moved there, the single sign-on, so we really needed to put in place some sort of automatic mechanism to perform failovers because there was none. At that point, the only thing that we had was just a replica, and if something happens, either you recover the primary in time or you promote the replica, but if this happens during the night, the operator calls you and the response time is critical for critical services. So this was the initial approach, just benefiting from ProxySQL built-in monitor, that decides where to route the traffic based on the read-only or super read-only variables, and from its scheduler module, we wrote some custom scripts to do the failover, the resolution of conflicts, and to fence out an instance when it was failing over. We added console as a source of truth because we didn't want to run our ProxySQL container with a network attached to it because of the problems that it might cause if you need to move it somewhere else. We are not using Kubernetes, we are using C-Corps Nomad. So just to avoid this storage layer, we decided to put some basic stuff in console, like who's the primary, who's the replica, and so on. The only problem with this approach is that it is not a real HA solution. It contains a single point of failure. Despite running in a container, there are situations where the proxy won't be spawned in another node and to have a downtime. It's not possible to deploy several proxies at the same layer for the use case that we wanted, because at the end, the proxy is not designed to take decisions on the topology it connects to. It is designed to route traffic, right? So we would need to implement some sort of consensus algorithm between the proxies if we wanted to keep the logic on the proxy layer. And yeah, at the end, maintaining all of these scripts would be an effort that having 4.5 people for maintaining this service was not affordable. So this is why in 2022 we went out again to the MySQL ecosystem and started looking into the different solutions. For our use case, we thought about the InnoDB cluster. We found it really easy to deploy and integrate with our infrastructure. At the end, group replication is a plugin that you can install in your regular setups. It also, what make us chose MySQL InnoDB cluster is the completeness of MySQL shell. We could automate with many scripts basic stuff like configuring the cluster or even rebooting the cluster for a complete outage was really simple for us. With leveraging the power of automation, we can dedicate ourselves to other stuff.
Do you just run 3 nodes or?
Yes, so far only 3 nodes. And one of them in the secondary data center.
Okay.
I mean, but it's not, we have like 9 3-node clusters because they are not super big. I mean, and it's better than what we had in the past. It's something that is evolving little by little. Because at the end, these are critical service and we don't want to rush into something really new that take unnecessary risk. So yeah, with this, we remove the single point of failure. It's a fully fledged HA solution that you don't need to put things together from different projects to make it work. But as I said, since we run MySQL with network attached storage, there is a particularity that we needed to have into account. Yes.
Do you use any sort of clustering, replication, etc. features in the storage, or are you doing it all in the database layer?
Yes. I mean, MySQL-wise, if we leverage the power of the replication in the storage.
Yes, but you can set up mirroring in NetApp storage and so on and so on. And if you do that, it would just replicate data.
No. We use the regular NGR. We don't use NetApp's replication. So as I was saying, the only problem that we had with this deployment is running databases with network attached storage. So from our experience running instances like that, it's like whenever there is for example, yes, one question?
Regarding the NetApp, but you have multiple NetApp machines always.
Yes.
Independent.
Yes. So the problem with this network attached storage is that, for example, there is now switch redundancy in the data center, but there was a time that there wasn't switch redundancy. And although having switch redundancy, there can be a patch applied to all the switches that brings them all down. So you have a network cut between the storage and the server. Also, during NetApp upgrades, these are rolling upgrades. The IP of one of the filers is failover to the next while it is upgraded. So if this process is too long, MySQL will hang, will freeze. And in this situation, what we have found is that 2 things can happen. Either it will perform a crash recovery once the connectivity is regained, or this process enters in zombie state, which leads you to reboot the whole host. Group replication doesn't see this as a failure. This we talked with the Oracle MySQL developers, and this is named as a gray error. So what we had to do was write our own systemd service that probes continuously the storage, and if during 5 different iterations, 5 consecutive iterations, it cannot ping the storage, then it will kill the instance, and group replication will take care of promoting the correct replica.
What's your average data set size in these clusters?
It varies.
If you can share out
It varies. At the end, it's scattered. So you don't really look into each database. For example, today we migrated the single sign-on, and it's only 45 gigabytes. It's a small database.
Are you not, when you do multiple terabytes, or just curious of, I mean, MySQL can handle inverted commas up to 100 terabytes, but you don't want to do that.
No, so far we don't have MySQL with GR that big. I guess the bigger is like 500 gigs or something like that.
Okay, is there a reason to start with network storage?
Yes, there is an historical reason. As I said earlier, we are also running Oracle databases. The Oracle databases, historically it was decided that we would purchase NetApp, and Oracle uses DNFS instead of NFS, so it works fine. And the cost of having DBOD inside the already purchased storage, it was negligible. So for us, it's a matter of economy, right? We're not a company selling products. We just receive money from the governments, and we have to get by with that. So yeah, as I was saying, when you run a service with more than 1,000 instances with few people, you need to automate as many things as possible. Otherwise, any task that is manual and repetitive is devoid of enduring any value to the team and scales linearly as your service grows. So I divided these automations into parts: web automation and operations automation. We decided to expose functionality of our service through a web instead of an API, partly because an API can cause big damage. Imagine a user that accidentally creates a loop and it's creating backups every 5 minutes. This will exhaust your storage, right? If you don't put in place some constraints. So that way you make sure that the user won't be doing that. Some things that we have enabled through the web interface are simple, like starting or stopping the instance, creating backups, and so on. We have also some more complex stuff like cloning or the integrated logic for upgrading primary replica cluster or InnoDB clusters, because the user don't always know which is the correct order and they might wreck the replication setup. And then behind the scenes, we have operations automation. These are things that are not visible to the user, but that make the service quality a better service, let's say. One that I wanted to highlight is, for example, the continuous validation of backups. We take snapshots, NetApp snapshots every day of our instances, and then we have we keep the last 30. We have then a service that for each production instance takes the full backup, uploads it to a secondary location, and this creates a task in a queue. Then there is a restore service that takes that task from the queue, performs a recovery, and rolls forward between 1 and 3 hours of bin logs to make sure that when you need those backups, they are really useful, right? That you're not keeping backups that are corrupt. Since I have 5 minutes left, I will skip to the next. Yeah. So another thing that we have introduced in the web is the automation of the upgrades. So before having this, what we would do when MySQL was releasing a new version, we will just integrate it in our infrastructure, testing one of our ref instances, which was empty, a toy instance. And then if the procedures were working for our toy instance, then we enable it universally. This is not a good approach because afterwards you would have tickets from users complaining because they didn't read the documentation, they didn't change this variable, this other. So with the MySQL shell, it comes a nice utility that is the upgrade checker. So what we do is we run the upgrade checker in a container. We copy the myCNF of the target instance into the container storage, and the container itself will connect to the instance. We'll go through the runtime variables and the myCNF variables, and we'll throw a report. This report is shared through our internal Dropbox with the user and the group of users that are allowed to manage this instance, and the upgrade won't be enabled until they correct all the upgrade checker errors. And this way it's safer to upgrade, let's say. And yes, one last automation that I wanted to share with you is the deprecation of UTF-8 and D3. This is something that, despite having been publicly published to our users, and we have installed it, but this needs to disappear because at some point MySQL will remove it. There was not a strong effort. They were not active, so we decided to put in place an automation to help them with this. The automation has two modes. One is a dry run that will only generate the DDL of the statements that will be executed to perform the changes. And the other one is the active run, let's say, that will create the DDL before and after the changes. We always recommend our users to create clones of their instances if they can do it from the web, so they don't find surprises like this one that was documented in this nice Percona blog by Speta. Yeah, that's all I have.
Did you look at the next steps from the cluster, like cluster set, read replicas and stuff like that? Will you implement these?
That will come. I mean, one of the things that I didn't mention is that within the cluster it's easy to scale out reads. We have setups now with primary replica where the replica is only used for reads, so this setup would disappear in favor of InnoDB cluster. Cluster sets would be also interesting, but at the end you have semi-synchronous replication between the clusters, right? So there might be some data loss at some point. What we would like to explore also in the near future is deploying in Kubernetes, because for PostgreSQL there is only the possibility of having HA without being too convoluted in Kubernetes. So maybe moving everything to Kubernetes instead of VMs and bare metals would be the we'll see.